A remark on I-open sets. Maybe you remember that there were at least 2 videos on our channel about I-open and I-open sets in standard topological spaces. And there was a question posed a few days ago by one of the channel's viewers, Musa Al-Ammar, if I'm correct. So thank you very much for your activity. Somewhat simple question. Is it true that every open set in a topological space is I-open too? Let us think about this problem for a moment. As for the I-open sets, they've been introduced perhaps in 2012 and then analyzed in next years by Sabi Ashkandar and Amir Mohammed, both from Iraq. And the definition of this class of sets goes as follows. A subset A, arbitrary subset A of X tau of some topological space, is said to be an I-open if there exists an open set G that is different than empty set and then the whole universe, such that our A is contained in the closure of A intersected with G. Okay, this is our definition. And the authors prove that there are I-open sets that are not open, but they state that every open set is I-open. The converse is not true, but they say that every open set in a topological space is I-open too. And the statement is then repeated in some other papers. So I think that there is a little mistake in the statement. Let us analyze the very concept of open sets and the very concept of I-open sets. Well, if we think about open sets in an arbitrary topological space, one could say that there are 3 basic types of open sets, namely the empty set, the whole universe, and all those sets that are non-empty and properly contained in X. So now assume that our open set is empty. Is it I-open? Well, one could say that we can take any G that is open, that is different than X, and of course, well, different than empty set by very definition, and it will be true that our empty set A is contained in the closure of empty set intersected with G, which is identical with the closure of empty set, which is empty. Empty is contained in empty. However, we must be sure that our space is not antidiscrete, that our topology is not of the following form. It should contain more sets than just empty set and X, because in antidiscrete space there is only one non-empty open set, but the set is X itself, while G should be different than X by the very definition. Yes, it was here. So the empty set is I-open if and only if our space is not antidiscrete. If our A is open and A is different than empty set and X, then we can take A as G. So of course then we have A is contained in its closure, yes, and this closure can be presented as A and A, but this is exactly our A and G. Yes, so yes, indeed, if our A is a proper open set properly contained in X and non-empty, then yes, it is I-open too. No problem. And the third case, the last one, assume that A is X, is the whole universe, the universal set. Then, for any set G, so in particular for any open G different than empty set in X, we have that the closure of A and G, so the closure of X and G, is like the closure of G, because X intersected with G gives us G, of course. But we want to obtain the following thing, that our A, namely X, is contained, well, exactly in this closure. So it means that closure of G must be X itself, because X is contained only in X. There are some sets that have this feature that their closure is the whole space. These are dense sets, yes? So it means that G should be dense and open, of course, by the definition of I-open set. But you see, there are some spaces where dense sets, in particular open dense sets different than X, do not exist. For example, take any discrete topological space. In discrete topological spaces, every subset of X is considered as open. Every subset. Everything is open. So everything at the same time is closed. Then every subset is closed too, and it's identical with, because it's closed, then it's identical with its closure. This is typical for topological spaces. This is not obvious in some, and not necessary in some weaker spaces like infra, supra, minimal structures, and so on, but in topological spaces, if it's closed, then it's identical with its closure. So in discrete topological space, the only subset G, such that the closure of G is X itself, but X cannot play the role of G in the definition of I open set. So we can say that X is I-open if and only if there exists at least one dense and open subset G of X that is different than X. You can think about further characterization about spaces. Maybe, I don't know at the moment if there are any spaces that, for example, are not discrete, but there are no open dense sets different than X, maybe. So I would say that this is a new characterization of open and I-open sets in the context of the question posed by our viewer. Then this is bibliography, so here you have one paper about I-open sets in the context of separation axioms, then I-open sets that are some extension of I-open sets, and another paper on I-separation axioms. Thank you very much for your attention.